Hi, hello everyone. Good evening to all of you. Welcome to ACE Engineering Academy. So in this session, we are going to see one of the important concept of computer network subject. So as part of computer network subject, in this session, we are going to see one concept from transport layer. So the transport layer functions, if you consider, transport layer functions, if you consider, like the PDUs of transport layer, we call them as segments. So transport layer is our heading here. And the functions, if you consider, the first point is PDU. PDUs of transport layer are segments. And this transport layer is responsible for congestion control. It is responsible for congestion control. And this transport layer is also responsible for connection management. It is also responsible for connection management. And transport layer is also responsible for error control. And transport layer can also do flow control. It is able to do flow control. And transport layer performs segmentation and reassembly. Segmentation and reassembly. And transport layer provides port addressing. You can say this is the seventh one, port addressing. And this transport layer also provides process to process delivery. Process to process delivery. So these are all the functions of transport layer. Among all these functions of transport layer, the most important topic is congestion control. This is the most important topic. So in this session, we are going to see what is this congestion control of transport layer. Okay, right. So coming to this transport layer congestion control, if you consider this is the sender system, if you consider this is the sender system, let's say this is a sender, okay, this is the sender. And if you consider this is the receiver, this is the receiver. So as you know that the TCP is a connection oriented protocol. So what is the meaning of connection oriented protocol? Before doing the data transmission, it requires connection establishment. After data transmission, it releases the connection. So by the time of connection establishment, this receiver is advertising his window size to the sender. Right? By the time of connection establishment itself, this receiver can inform to the sender like this much amount of buffer I am having, means it is advertising his window size to the sender by the time of connection establishment phase itself. So for example, if the receiver buffer size is, let's say the buffer size of the receiver is, assuming that 1 MB. If the receiver buffer size is 1 MB, and if as you know that transport layer PDUs are segments, so that the segment size, if you consider, the size of the segment is 1 KB. So the receiver buffer size is 1 MB and the segment size is 1 KB. Then as part of this receiver buffer size, as part of this receiver's buffer, how many number of segments can be part? How many number of segments can be part? Tell me. So this is this is buffer size by which is BS, buffer size by segment size. What is the buffer size? 1 MB. 1 MB, how can I write? 2 power 20 by 1 KB, how can I write? 2 power 10. So which is going to be 1024 number of segments. So the buffer of the receiver can have 1024 bytes of data, 1024 segments. 1024 segments are part of, or else this buffer of the receiver can accommodate 1024 number of segments. So this buffer size, okay, so what is this receiver's buffer size? 1024 number of segments I can receive. This information, this receiver has already informed to the sender at the time of connection establishment. Now this sender okay, this sender. So since he knows the capacity of the receiver, since he knows the buffer size of the receiver, he starts transmitting 1024 number of segments. So now the sender is transmitting 1024 number of segments like this. So he is transmitting 1024 number of segments. Like for example, segment 0, segment 1, and so on, segment 1023. So like this, he keep on sending the segments to this receiver. But from this receiver, this sender is not getting any acknowledgement. The reason why the sender is not getting the acknowledgement from this receiver, in the sense the receiver have not received these segments. So as the receiver does not get, as the receiver have not received any segment, this receiver is not sending the acknowledgements. And on other hand, this sender is thinking like I have already transmitted according to the receiver's advertised window. According to the receiver's advertised window, I have transferred 1024 number of segments. Then even though I am not getting the acknowledgement within the timer, why? So like that, this sender is keep on thinking. On other hand, this receiver is keep on thinking like I have announced my advertised window to the sender, but why the sender have not yet started the data transmission? And you know, this sender, since he is not getting the acknowledgement within the timer, what this sender will do? He will do again retransmission of 1024 number of segments, because you know that TCP is a reliable connection oriented protocol. So reliable means what? For every data transmission, acknowledgement expectation. That is what the TCP sender's behavior. So as a reliable protocol, it is a reliable protocol. The TCP is a reliable protocol. So it is always expecting the acknowledgement. So if it is not getting the acknowledgement within the timer, then the TCP sender can retransmit the segments. So since he is not getting the acknowledgement within the timer, this sender will do again retransmit all these 1024 number of segments. Again he sets the timer, again he is not getting the acknowledgement, again he will send the 1024 number of segments. So like this, he is keep on sending, retransmitting 1024 number of segments. If it is being continued, then there is a possibility for system crashes, because keep on sending the messages, right? So there is a possibility for system crashes. And according to the sender, is there any mistake from the sender end in the sense? No. Reason? According to the receiver's advertised window, the sender have transmitted the data. He is not sending the segments more than that 1024 number of segments, he is not transmitting. According to the receiver buffer, what is the receiver buffer? 1024 number of segments. So those number of segments are keep on sending by this sender, but he is not getting the acknowledgement. On other hand, this receiver, he is in thinking, like he is in thinking process, like I have announced my buffer size to the sender at the time of connection establishment itself, but why I am not getting any segment from the sender? So like this, these two are thinking, but no one is having the mistake. So he has advertised his window, and according to the advertised window of the receiver, he has transmitted the data, but he is not getting the acknowledgement, and he has not yet received any data segments. Then where is the problem? So why the sender is not getting the acknowledgement within the timer, and why this receiver is feeling that why the sender have not transmitted the data, but actually the sender have transmitted the data. But why the receiver is not getting the segments here? So there is some problem. What is that problem? Intermediate between the sender and receiver. Between the sender and receiver, we are having an internet here. So we are having an internet here. So this internet is having so many number of routers. This internet is having so many number of routers. You know that those routers are having buffers. So since this sender is keep on retransmitting the 1024 number of segments, you know, this internet got congested. So since there is a congestion in the internet, this receiver does not get any segment, and since he is not received any segment, he won't send the acknowledgement, and this sender always keep on waiting for the acknowledgement, but he never gets the acknowledgement now. So where is the problem in the sense? The problem is with the internet. So at this internet, the congestion is occurred. So this information is, I mean, this research, let's say this research or else this problem is identified by a person called Jacobson. So Jacobson have invented this entire scenario. So what this Jacobson have done, so now this is the buffer size, which means that I can say receiver's window size I can call, receiver's window size I can call. And this Jacobson have proposed a congestion window to this internet. So to this internet, the Jacobson have proposed a congestion window with the initial size of 1. Then this sender should transmit the data according to congestion window as well as the receiver window. It means that this network should not face the congestion and this receiver also should not get any problem. Accordingly, he needs to transmit the data. Then the sender window size is being calculated like minimum of among these two, congestion window and the receiver window, among these two, the minimum, what is the minimum value? That minimum value can be transmitted by this sender. So this is the way how the sender is doing the transmission here. So the solution is being proposed by this Jacobsons here. So which means this is what the fundamental concept, the fundamental or as the background to understand what is exactly this transport layer congestion control. So now how this congestion control is being handled by transport layer, that is what my next point. So transport layer, or else you can say that the TCP can handle the congestion, TCP can handle the congestion in 3 phases, So what are the 3 phases it is having, you know? So they are, the first one is slow start phase, and the next one is additive increase phase, and the next one is additive increase phase, and the next one is multiplicative decrease phase, So in these 3 phases, this transport layer can handle the congestion. So here, this additive increase phase, you can also call it as, congestion avoidance phase. This is congestion avoidance phase. And this multiplicative decrease phase, you can also call it as congestion detection phase. So what exactly this slow start phase, what exactly this additive increase phase, and what exactly this multiplicative decrease phase? This we are going to see. So for example, if you consider first slow start phase, So what is the first point we can write here is, the sender calculates the congestion window, sender calculates the congestion window to the receiver with initial size of 1 segment, The sender calculates the congestion window to the receiver with initial size of 1 segment. Then look at. So after transmission of 1 segment, the congestion window size becomes 2. After transmission of 1 segment, the congestion window size becomes 2. So similarly, after transmission of 2 segments, the congestion window size becomes 4. Next, after transmission of 4 segments, the congestion window size becomes 8. So this way it is going on. I mean, this is having some kind of growth here. So if you observe, initially it is 1 segment, but after transmission of 1 segment it is becoming 2. After transmission of 2 segments it is becoming 4. After transmission of 4 segments it is becoming 8. So it seems, so I can write like this and so on. So then what is the point I can write? This is the important point here. What is the point I can write here? It seems there is an exponential growth, in congestion window size, There is an exponential growth in the congestion window size. So this exponential growth is continued. So this exponential growth in congestion window, this exponential growth in congestion window is continued, in congestion window size is continued until reaching the congestion threshold, So until reaching the congestion threshold, there is an exponential growth in the congestion window size. So the exponential growth, I can write here growth. The exponential growth in the congestion window is continued until reaching the congestion threshold. So this is what your slow start description. So look at what we can have here. So transport layer can do congestion control in 3 phases. That is, first one, slow start phase, additive increase phase, and multiplicative decrease phase. And if you look at the slow start phase, initially the sender is calculating the congestion window to the receiver with the size of 1 segment. After transmission of 1 segment, the congestion window size becomes 2. After transmission of 2 segments, the congestion window size becomes 4, and so on. So it seems that there is an exponential growth in congestion window size. So this exponential growth in congestion window size is continued until reaching the congestion threshold. So this expression, this entire theory we are going to see in terms of a simple diagram like this. So initially the sender is calculating the congestion window with 1 segment. After transmission of this one segment, see here 1 segment is being transmitted. After transmission of this 1 segment, he is getting the acknowledgement, then the congestion window size is becoming 2. So now this is called 1 RTT. Then now in the next transmission, the sender can transmit 2 segments. Now he has transmitted 2 segments. This is the first segment and this is the second segment. For both of them, we are getting acknowledgement. So then this is my second RTT. So after this second transmission, the congestion window size becomes 4. Then now we can transmit 4 segments. So look at, we have transmitted 4 segments here. So after transmission of 4 segments, we got 4 acknowledgements and the congestion window size is becoming 8. So it means that if you verify, initially the congestion window size is 1, which I can write as 2 power 0. After transmission of one segment, the congestion window size becomes 2. This I can write as 2 power 1. And after transmission of 2 segments, the congestion window size becomes 4, which I can write as 2 square. After transmission of 4 segments, the congestion window size becomes 8, which I can write as 2 power 3. So if you verify this, this is an exponential growth in the congestion window size. So this analysis in 4 steps we can see like this. At the start of slow start phase, the congestion window size is 1. After the first RTT, the congestion window size becomes 2. After second RTT, the congestion window size becomes 4. After third RTT, the congestion window size becomes 8. So it seems there is exponential growth. Look at, initially it is 2 power 0, then 2 power 1, 2 square and 2 cube. This is called exponential growth in the congestion window size. So this exponential growth in the congestion window size is continued until the congestion threshold. So once the congestion window size, once the exponential growth in the congestion window size is reaching to the congestion threshold, then what will happen? Additive increase phase is going to be started now. So that is what my next concept here. So what is the next I am going to see? Additive increase phase now. So far we have seen slow start phase. Now we are looking at additive increase phase. Additive increase phase. AI phase, I can say. So in this additive increase phase, what is the first point we can write? Once the exponential growth in congestion window size is reached to the congestion threshold. Once the exponential growth in the congestion window size is reached, okay, once the exponential growth in the congestion window is reached to the congestion threshold, from that moment onwards, there is a linear growth, in congestion window size. There is a linear growth in congestion window size. So this linear growth in congestion window size, is continued until the timeout occurs, or the maximum window size is reached. Until the timeout is occurred or the maximum window size is reached. So this is what your additive increase phase points, and this is called congestion avoidance phase. So look at these points here. Congestion avoidance phase. Once the congestion window size reaches to the congestion threshold, from that moment onwards, there is a linear growth in the congestion window size. And this linear growth in congestion window size is continued until timeout occurs or the maximum window size is reached. Okay, right. So then we can see, for example, in our previous case, in our previous slow start phase diagram, if we verify, assuming that the congestion threshold value is, the congestion threshold value is, let's say 4. Just assumption that this is the congestion threshold value. Just assumption, okay? This is your congestion threshold value. So how we can calculate the initial congestion threshold value, in the sense, the initial congestion threshold is equals to the receiver window size by 2. The initial congestion threshold value is receiver window size by 2. Okay? So, for example, in our example, we are considering the congestion window size is 4, right? So now look at. So now we have reached congestion threshold. Just assuming that we have reached congestion threshold. So now it means that in the next transmission, how many segments we can transfer? In the next transmission, we can do 4 segments. But how many segments after transmission of that 4 segments? Then what can be the window size? If it is a slow start phase, it becomes 8. But since it is additive increase phase, and we have considered that the congestion threshold value is 4. So since we have reached the congestion threshold value, after transmission of 4 segments, the congestion size becomes 5, linear increment. And the most important points here is, if you consider this slow start phase, look at the points, important points. These are the important points. If you observe, For every 1 RTT, these are the very important points. For every 1 RTT, the congestion window size is becoming doubled, right? So for every 1 RTT, for every 1 RTT, the congestion window size is doubled. Very important. Look at, before this RTT it is 1, but after this RTT is becoming 2. Now we have transferred 2 segments, but after this RTT it is becoming 4. For every 1 RTT, the congestion size is getting doubled. Next, and one more important point. What is that one more important point? For every acknowledgement, for every one acknowledgement, let's say for every one acknowledgement, there is a linear growth, in congestion window size. There is a linear growth in the congestion window size. Look at, for example, 2 segments is being transmitted. After transmission of 2 segments, for example, just follow this. After 2, these are the 2 segments you have transferred. Now this is the segment which you have transferred, and you are getting acknowledgement. After this acknowledgement, what can be the window size? The window size is going to be 3. 1 segment gets added. Linear growth. After receiving 2 segments, the congestion size is becoming 4. So means for every 1 RTT, the congestion size is becoming doubled, but for every 1 acknowledgement, there is a linear growth in the congestion window size. These 2 points are, please mind this. This is what happening in your slow start phase of TCP. But when it comes to additive increase phase, just if we consider additive increase phase, here we are considering that in this additive increase phase, we are considering that congestion threshold value, we have mentioned 4, right? We have mentioned 4. Just assumption it is. Assume that the congestion threshold value is 4. So now this is the sender and this is the receiver. So we have reached the congestion threshold value. Look at, we have reached the congestion threshold value, which is 4. Now, how many segments I can transfer? 4 segments. Look at, the first segment is being transmitted, receiving the acknowledgement. Second segment is being transmitted, receiving the acknowledgement. Third segment is being transmitted, receiving the acknowledgement. And fourth segment is also transmitted, which is receiving the acknowledgement. So now this is one complete RTT. So after this one complete RTT, what is happening? As it is the congestion threshold value, after transmission of 4 segments, the congestion window size becomes how much? Is it 8 or else 5? It is how much? 5. Linear growth. So for every 1 RTT, the congestion window size is getting incremented by 1. That is what the important point here. In additive increase phase, for every 1 RTT, the congestion window size is increased. By one segment. For every 1 RTT, the congestion window size. For every 1 RTT, the congestion window size is increased by 1. But in the case of slow start phase, for every 1 RTT, the congestion window size is being doubled. The congestion window size is getting doubled. But here, incremented by 1 segment. Then, for every 1 acknowledgement, this is the important point. For every 1 acknowledgement, what is the change in the, how much amount of increment you can find in the congestion window size? For every 1 acknowledgement, the congestion window size is increased by 1 by WC. So if you verify here, how many segments you have transferred? 4 segments. So when you have transferred 4 segments, let's assume that you have received this first acknowledgement. So when it is received first acknowledgement, 0.25, 1 by 4, which is 0.25 amount of window gets increased. then second acknowledgement is being received. Then again by that moment, again 0.25 amount of increment you can find in the congestion window size. It means that, let's say the questions can be like this. In the additive increase phase of TCP, assume that you have sent 4 segments. Now you have received at some point of time, you have received 2 segments, then 2 acknowledgements. After receiving 2 acknowledgements, what is the window size? What is the resultant congestion window size? This type of questions are possible. Then what is the resultant window size? As you have transferred 4 segments, already 4 segments are there, then for 2 acknowledgements you have received. 2 acknowledgements in the sense 0.25, 1 growth you can find in the congestion window, and 0.25 growth you can find in the congestion window. So 0.25, 0.25, it becomes 0.5. So means that 4.5 is the congestion window size after receiving 2 acknowledgements. After receiving 3 acknowledgements, the congestion window size is becoming 4.75. After receiving 4 acknowledgements, then the congestion window size is becoming 5, 1 segment. So for every 1 acknowledgement, the congestion window size is incremented by 1 by WC. These are the very sensible points. Straight previous year gate questions you have based on these points. So this is what your additive increase phase. Look at those in additive increase phase points. If you consider this one. The congestion threshold you are considering, here 4. The congestion threshold you are considering as 4. So now you are transmitting 4 segments. After transmission of 4 segments, you are getting 4 acknowledgements, fine. But what is the resultant congestion window size? 5. Now you have transferred 5 segments and you are getting 5 acknowledgements. Then what is the congestion window size here? Look at 6. 1 segment gets added. 1 segment gets added. This is called linear growth in the congestion window size. For every 1 RTT, the congestion window size is incremented by 1 segment. Okay, but for every 1 acknowledgement, the congestion window size is incremented by 1 by WC. This is what the observation you can do with respect to your additive increase phase of TCP. Then look at the start, your congestion window size, for example, I means let's say 4. Then after 1 RTT, it is becoming 5. After 2 RTTs, it is becoming 6. After 3 RTTs, it is becoming 7. Means 1 segment is getting added, increment, linear increment. You can find the linear increment in the congestion window size. So this is what your congestion avoidance phase. So the linear growth in the congestion window size, what is the last point we have seen in the congestion avoidance phase, which is additive increase phase? The linear growth in the congestion window size is continued until timeout occurs or the maximum window size is been reached. Now we are going to see, for example, multiplicative decrease phase. So far we have discussed about additive increase phase. Now we are moving to multiplicative decrease phase. Multiplicative decrease phase. So coming to this multiplicative decrease phase, first point, this multiplicative decrease phase I can consider as congestion detection phase. I can consider it as a congestion detection phase. Congestion detection phase. So the point here is when the timeout is occurred. So we have mentioned now the linear growth in the congestion window size is continued until timeout occurs. Now we are looking at that timeout. So when the timeout is occurred, so this timeout is, stronger possibility for congestion. Stronger possibility. This timeout situation is called stronger possibility for congestion. So when there is, what is the meaning of stronger possibility of congestion? The meaning of stronger possibility of congestion is, if you consider this is a sender and if you consider this is a receiver, first segment is being transmitted, second segment is lost. Then third segment is also not reaching, fourth segment is also not reaching, fifth segment is also not reaching. If 1 segment is lost, all further segments are not reaching to the receiver. This kind of situation is called stronger possibility for congestion. And there is one more case you are having in the multiplicative decrease phase. Let's say this is, you can consider as case 1. you are having one more case. What is that one more case? The one more case is your 3 duplicate acknowledgements. 3 duplicate acknowledgement. So this 3 duplicate acknowledgement is called as weaker possibility for congestion. Weaker possibility for congestion. Weaker possibility for congestion. Weaker possibility for congestion. So whatever the diagram I have drawn here, this is stronger possibility for congestion. But what is this weaker possibility for congestion? Look at, so the weaker possibility for congestion is, for example, if you consider this is the sender and if you consider this is the receiver, the sender have transmitted the first segment, then the second segment is also transmitted, but the second segment is lost. Then the further segments are being reaching to the receiver. One segment is lost, but further segments are successfully reaching to the receiver. So for every, so now this segment is being reached, then one acknowledgement can be coming here, and one acknowledgement can be coming here, and one acknowledgement is coming here. This acknowledgement is about this second segment. Let's say if your segment size is 100 bytes, or else let's say 100 bytes, then the first segment is having 0 to 99 bytes, and the second segment is having 100 to 199 bytes, and the third one is having 200 to 299 bytes, and the fourth one is having 300 to 399 bytes, and the fifth one is having 400 to 499 bytes. But after receiving this 200 to 299 segment, what can be the acknowledgement you can have? The acknowledgement is acknowledgement 100. After receiving this 300 to 399, what is the acknowledgement you can have? Acknowledgement 300 again. After receiving this 400 to 499 segment, again the acknowledgement can be 100. So look at 3 times of acknowledgement with the same sequence number. 3 times of acknowledgement is being arrived. So when the 3 types of acknowledgement, 3 sequence number, the acknowledgement is being generated for 3 times with the same sequence number. So that is what your 3 duplicate acknowledgement. So after one segment is lost, the subsequent segments are successfully reaching to the receiver. This is called weaker possibility for congestion. But after one segment is lost, if the subsequent segments are not reaching to the receiver, that is called stronger possibility for congestion. So if there is a timeout case, means stronger possibility for congestion. Look at timeout. If there is a timeout case, what is the changes we are doing here? If there is a timeout case, what is that timeout case? Stronger possibility for congestion. What is the meaning of stronger possibility for congestion? Is a segment has probably been dropped in the network and there is no news about the following sent segments, means the following sent segments are also getting lost. That is called stronger possibility for congestion. Then what will happen? The congestion threshold value can be calculated by setting to the current congestion window size by 2. This is the first step that can be taken by TCP. And then it is resetting the window size to initial value, that is 1 segment. And then again it is asking you to start from slow start phase. But if it is weaker possibility for congestion, that is your 3 duplicate acknowledgements. So this is called weaker possibility for congestion. So what is the meaning of weaker possibility for congestion? A segment may have been dropped, but some segments after that have arrived safely. Some segments after that have arrived to the receiver safely. So this type of situation is called weaker possibility for congestion. So when there is a weaker possibility for congestion, you know that that particular situation is also called as fast retransmit and fast recovery phase. When there is a 3 duplicate situation, 3 duplicate acknowledgement situation, then same here also, first we need to set the congestion threshold value for half of the current congestion window size. After that, you need to set your congestion window size to congestion threshold. And then you need to start additive increase phase, not slow start phase. This is the way in both cases, like stronger possibility for congestion and weaker possibility for congestion. In both the cases, the TCP can react in these 3 steps. So if it is stronger possibility for congestion, first initiation that is taken by the CP is, first condition that is taken by the TCP is setting the congestion threshold value to the half of the congestion window, and then it is initializing the congestion window size to the one segment, and then it is asking us to start slow start phase if it is stronger possibility. But if it is weaker possibility, first step is same. What is the first step? Setting the congestion threshold value to the current window size, half of the current window size, current congestion window size, and then congestion window size is being set to congestion threshold, and then it is asking you to start additive increase phase rather than slow start phase. So this is what the theory portion of your TCP congestion control. So based on this information, whatever the information we have, so based on that information, we are having some previous year gate questions. Look at, so whether to solve those questions, is it sufficient information or not, verify. This is the question which we have in 2008. Look at, in the slow start phase of TCP congestion control algorithm, the size of the congestion window, slow start phase, what kind of growth you can see in the congestion window size, which is exponential growth in the congestion window size. D, straight question. Next, look at the next one more question based on this congestion. Yeah, look at this question. So consider the following, this is given in 2018. Consider the following statements regarding the slow start phase of TCP congestion control algorithm. Note that the congestion CWND stands for TCP congestion window and MSS denotes the maximum window size. First statement, the congestion window increases by 2 MSS on every successful acknowledgement. The congestion window approximately doubles on every successful acknowledgement. The congestion window increases by 1 MSS on every round trip time. The congestion window approximately doubles on every round trip time. Which one of the following is correct? Option A, only 2 and 3 are true. Option B, only 1 and 3 are true. Option C, only 4 is true. And option D, only 1 and 4 are true. So what can be the answer for this question? So if you verify the first statement, the congestion window increases by 2 MSS on every successful acknowledgement. Is it true? No, it is false. On every successful acknowledgement in the case of slow start phase, in the case of slow start phase, for every one successful acknowledgement, the window size gets incremented by 1 segment, but not 2 MSS. Hence, it is false. The congestion window approximately doubles on every successful acknowledgement. No, it is not. So on every one RTT, the congestion window size gets doubled, but not on every successful acknowledgement. Hence, the second one is also false. Look at the third one. The congestion window increases by 1 MSS on every round trip time. No, on every round trip time, the congestion window size is getting doubled. Next, the congestion window approximately doubles on every round trip time. So this is also false. But if you look at the fourth statement, the congestion window approximately doubles on every round trip time. Yes, it is true. So among the 3 statements, as only the fourth statement is true, you can say option C is the answer for this question. Only fourth one is true. So these type of questions we can have, theory-based questions based on this TCP congestion control. Let's see one question, one numerical question based on this TCP congestion control. Simple question. In the slow start phase of TCP congestion control, the current congestion window size is 4 MSS. And the sender gets 4 successful acknowledgements of segments. Then what should be the value of congestion window? So it is clearly mentioned that it is a slow start phase. And how many acknowledgements you have received? 4 acknowledgements. So the congestion window size is 4 MSS. And 4 successful acknowledgements. Let's say first acknowledgement is being received, then how much growth you can find? 1 MSS, because 1 segment gets added. We mentioned, no, there is a linear growth. For every successful acknowledgement, there is a linear growth in the congestion window size in the case of slow start phase. But for every round trip time, the congestion window size gets doubled in the slow start phase. But in the case of additive increase phase, for every round trip time, for every 1 round, the congestion window size is incremented by 1. But for every 1 successful acknowledgement, the congestion window size is getting incremented by 1 by WC value. So as it is slow start phase, for every 1 successful acknowledgement, the congestion window size is incremented by 1 segment. So this is first acknowledgement, 1 segment. Now second acknowledgement, 1 segment. Third acknowledgement, 1 segment. Fourth acknowledgement, 1 segment. So then, after receiving 4 acknowledgements, what is your congestion low size if you verify? 4 MSS, 5 MSS, 6 MSS, 7 MSS and 8 MSS. After 4 successful acknowledgements, your congestion low size becomes 8 MSS, which is option B is the answer for this question. So like this, you can have more and more questions based on this TCP congestion control. I hope this session is helpful to you, and this is one of the most important concept as part of transport layer of congestion control. Okay, so this is one of the more important concept of transport layer. I hope this session is helpful to all of you. Thank you.
You have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi. And I have secured All India Rank 1 in ESE 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESE 2020 and ESE 2021.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESE 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of interview panel. It has helped me in my success.
Myself Abhishek Kumar Sharma. I have scored All India Rank 1 in UPSC Engineering Services Examination 2021 in Electrical Engineering discipline. Now I divide my preparation strategy into 3 basic things. The first thing is that you have to complete your syllabus from a basic standard source. The second thing is that you have to attempt previous year question. The third thing aspirant has to do is to solve as many test series as possible. I made 2 to 3 pages short notes of each and every subject. Now 2 to 3 pages short notes help in quick revision. If you keep working hard, you will definitely get success in this examination. This is what I followed, and I wish all the best for all the future aspirants. Thank you.
My name is Kuldeep. I have done my BTech from Ambedkar Institute of Technology, which is situated in Delhi. And I have secured All India Rank 1 in ESE 2021 from E&T branch. I took ACE Postal Course, Mains Test Series and Interview Guidance Program in ESE 2020 and ESE 2021.
Hello everyone, my name is Karthikeya Kaushik and I have secured All India Rank 1 in UPSC Engineering Services Examination 2021 from Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESE 2021. I have been associated with ACE Engineering. I have taken various programs like Life's main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also